Dear students, today we will discuss the 1 hour skita rule limitations. The 1 hour skita rules is limited for the compounds of alkyl cyclohexanols. The boiling points of the alkyl cyclohexanols not is with accordance with the 1 hour skita rule. 1 hour skita rule fails to explain the boiling points of alkyl cyclohexanols. We have the examples of there is the 2-alkyl cyclohexanol, that is a cis and trans isomers. The 1 hour skita rule, we have stated that any alicyclic epimers which is having same dipole moment, the isomers having higher heat content. The higher heat content means the enthalpy shows higher boiling points, higher refractive index and higher density. This is our 1 hour skita rule. When we apply this rule to that compound, one of the cis compound and other is a trans compound, 2-methyl cyclohexanol. We have found the relation in previous lecture, the enthalpy. Okay, enthalpy or heat content. Okay, enthalpy is nothing but the heat content of a molecule is inversely proportional to the molecular volume. If molecular volume is less, then its enthalpy is higher, and as enthalpy is higher, then its refractive index is higher, density is higher, and also our boiling point will be higher. And if it is higher molecular volume, the enthalpy is less, and all these physical quantities will be less. This is a relation from the 1 hour skita rule we found. Therefore, the molecular volume for this compound is higher molecular volume. Higher molecular volume. And for this compound is lower molecular volume. Lower molecular volume. Because when the second molecules came together, same compound, then it should require the higher molecular pace, and for this compound it should require the lower molecular space, because one is at axial position, therefore the two molecules will come near to each other, and for these both groups are the equatorial, therefore the both these same types compounds are having the more pace required. Therefore it is having the higher molecular volume and it is have the lower molecular. Therefore lower molecular volume means if volume is lower, enthalpy is higher. Therefore for this compound enthalpy is higher. Therefore for this compound, if higher molecular weight, therefore enthalpy is lower. Enthalpy is lower. When we studied these compounds, all of its boiling points, refractive index, densities, the values we have summarized in this table. When we discuss about refractive index of our cis compound, Okay, refractive index of this compound is 1.4648 is equal to 1.4648, and for this compound refractive index is equal to 1.4613. okay, this is a trans compound because this CH3 group is at the lower side and OH is at the top side and this CH3 is at the bottom. Therefore the trans, EE trans, this molecule is the EE trans because CH3 is also equatorial position and OH is also at equatorial position. This is at axial position, this is equatorial position. Therefore it is a AE isomer. Okay, therefore it is a AE isomer. Okay, this is AE isomer. For AE isomer value is the 1.4648 and for EE isomer it is a 1.4613. Therefore enthalpy is higher, refractive index is also shows the higher, and its enthalpy is lower, refractive index is also lower when we compare with this AE isomer. Okay, for refractive index it follows the 1 hour skita rule. For second we discuss the density. Okay, density also, if enthalpy is higher according to the 1 hour skita rule, density is also higher. Therefore density of this cis compound is the 0.9356, and for this compound density equal to 0.9241. Therefore density value for AE isomer is 0.9356, which is higher than this density values of EE isomer. Therefore it is also matches with 1 hour skita rules. Okay, according to 1 hour skita rules, enthalpy is higher for this molecule, therefore its refractive index is also higher, density is also higher. Refractive index higher, lower, enthalpy is lower, therefore refractive index is lower and the density is also lower for this molecule when we compare the AE isomer or 2-methyl cyclohexanol with the 2-methyl trans isomer of 2-methyl cyclohexanol. Therefore, when we consider the boiling points of AE isomer, it becomes 165 degrees Celsius, and when we consider the boiling point this molecule, it is equal to 166.5 degrees Celsius. Okay, therefore enthalpy is higher, therefore we have considered as the boiling point should be higher according to the 1 hour skita rule. But actually you found that it does not follow the 1 hour skita rule. 1 hour skita rule fails to explaining the boiling points of alkyl cyclohexanols. Therefore, the boiling point of EE isomer, which is having enthalpy lower, is higher than the AE isomer. This is a limitation for the 1 hour skita rule. According to this rule, the alkyl cyclohexanols boiling points is not depends on or is not explained by using the 1 hour skita rule. All other properties like refractive index and density follows the 1 hour skita rule for the these 2 alkyl cyclohexanols and also these 2-methyl cyclohexanols. But when you consider the boiling points of 2 alkyl cyclohexanols or 2-methyl cyclohexanols give the answer why the boiling points is not accordance with or is not follow the 1 hour skita rule. This is one of the limitation for the 1 hour skita rule. Why this is happen? Because it's the answer is located in the its conformation. Okay, your that is the this isomer is your EE isomer. Okay, with this isomer, when you look that particular molecule, that is EE isomer, is the most stable isomers among all these isomers. Trans isomers is the most stable because these are the away from each other. This molecule forms the strong hydrogen bonds with other molecule. But this molecule, due to there is a steric crowding, not forms the hydrogen bonding, or less in forms the hydrogen bonding is there. But this molecule, the OH is CH3 and OH is away from each other, therefore hydrogen bonding in this molecule quite easy, and therefore due to hydrogen bonding the one molecule is attached to this molecule, therefore for separation of them large energy is required, therefore boiling points for this molecule is the higher. This is because of hydrogen bonding present in your trans isomers, because our methyl groups and OH groups are the away from each other. That is the reason for. Same condition is for cis isomer. When you consider the cis isomer for 1,3, okay, 1,3 methyl group and OH group at 1,3 position. When you compare with this, you can find that the cis isomer, its boiling point is higher than the trans isomer, but all other properties are the, in this case, lower property of refractive index, lower property of density, higher property refractive index, higher property. But when you consider its boiling points, it not, this is also the alkyl cyclohexane, its boiling points not follows the 1 hour skita rule. Okay, the compound you can show like that. When you consider the cis isomer of 1,3 cis isomer is like that. There is CH3 and the OH, that is the cis isomer. It shows the higher molecular volume than the other. Okay, this is our EE isomer of 1,3, and for and this is our EA isomer. Okay, this is a lower molecular volume. Okay, for this lower molecular volume means the higher enthalpy, and higher molecular means the lower enthalpy. Therefore, lower enthalpy, its boiling points also should have lower, but actually the boiling points of these AE isomers is higher than the EA isomer. But all other properties for these molecules, refractive index, density is shows the lower quantity, and its refractive index for AE isomer and density, it shows the higher values, but only changes appeared in the boiling points. Boiling points of alkyl hexanols, okay, alkyl groups and hexanols group is present in our cyclohexanol. The boiling points of these compounds is not follow the 1 hour skita rule. This follows the one. It gives the reading opposite to the 1 hour skita rule. This is all about the first limitation for the 1 hour skita rule. Now, 1 hour skita rules we stated as the alicyclic epimers, which is having the same dipole moments, and higher heat content isomers shows higher boiling point, higher refractive index and the higher density. But when we have the compounds which is having the different dipole moments, for that compounds we cannot apply the auwers skita rule. Okay, remember that. The isomers, epimers or isomers, alicyclic, okay, remember alicyclic isomers or epimers which is having the different dipole moment, these compounds shows the new rule, Van Arkel rule. Okay, according to this rule, the alicyclic epimers or isomers which is having different dipole moments. Okay, alicyclic epimers or isomers. Okay, alicyclic means the which is the cyclic compounds. Okay, like the cyclohexane, but it is not aromatic compound. It is an aliphatic compound, cyclic compound. It is not an aromatic compound. And epimers and isomers means it's looking same, but its structure is the different than the isomer. We call it as the isomers. And epimers is the compound where the different chiral center is there, and only one chiral center has the change in configuration. That compound, these two isomers are the epimers to each other. Therefore, alicyclic epimers or isomers which is having different dipole moment, the higher dipole moment compound shows higher values or higher physical properties. This is the second limitation for the auwers skita rule. For the different dipole moments, the new rule arises. That new rule is stated as the alicyclic epimers or isomers which is having different dipole moment. The higher the isomer which is having higher, in between this higher dipole moment, it shows the higher values of physical constants. This is the second rule, is stated as by the rule that is called as the Van Arkel rule. Now the conformational rule, okay, the your auwers skita rule is also called as the conformational rule. Therefore, the dipole moments, okay, by using this conformation rule, we can predict the conformations of alicyclic epimers or isomers. But instead of these rules, we have also the by studying the dipole moments or by studying the strength of acid, we can predict the structure of the alicyclic isomers. Suppose we have dibromocyclohexane compound, 1,2-dibromocyclohexane compound. Okay, this is one cyclohexane, and that is it shows the 4 isomers. First is our equatorial bromine group is there. Okay, this is a trans isomer. This is a trans isomer of 1,2-dibromocyclohexane. Okay, second isomer is at the X. Both position are at the axial position. Both bromine are at the axial position. Then second isomer is the one bromine at the axial position, and second is at the equatorial position. Therefore, one is at the axial position and second one is at the equatorial position. These are the 4 isomers associated with our 1,2-dibromocyclohexane. By studying the dipole moment of these compounds, we can found theoretically values of dipole moment. We can found for the AE isomers. Okay, when this carbon is overlapped with this carbon, therefore our conformation we can show like that. This is our bromine is at that side, therefore we show the bromine at that side. This group is that side, we show like that. Bromine is at that position. Okay, this is the at behind side. Bromine will be at this position, and this is, it looks like that. Therefore the dihedral angle between these two bromine is the 60 degree. Okay, dihedral angle decides the dipole moments. If the dihedral angle is the same, the dipole moment is same for all these compounds. Okay, there is one formula is there. By using this dihedral angle we can calculate the dipole moment. As our dihedral angle increases, dipole moment goes on decreases. Okay, very rough we can say that dipole angle increases, our dihedral angle increases, dipole moment also goes on increasing. Now for this compound, when you show this compound is overlap, this carbon overlap with this, you can show that the bromine is at this position, therefore we show that position is this position. Okay, and that's last hydrogen at the bottom, and behind is the bromine is like that, we show the bromine at this position, and all other position the hydrogen, and this position is like that. Therefore bromine, in this case this angle, dihedral angle is also 60 degree, therefore it's our theoretical dipole moment should be 3.09. For this also, because dihedral angle is the same, theta is the dihedral angle and it is same 60 degree. For this dihedral angle theta is the same 60 degree. Therefore dipole moment is, we have theoretically predicted also 3.09. For this compound, if you draw in a conformational form, then this overlap with this, then bromine is at below side, the bromine, and at this these two groups, and then this is at that side bromine. Okay, this and this. Okay, therefore you can see here also the dihedral angle between bromine and bromine is the theta is equal to 60 degree. Therefore we can theoretically predict that this our dipole moment should be 3.09. But when theta is equal to 180 degree, then dipole moment should be, theoretically by using the formula we can predict it is 0. Okay, theoretically we find out by using the theta. Okay, this theta are the same, therefore dipole moments theoretically we can predict it as the 3.09, 3.09, 3.09. For the theta is equal to 180, the dipole our dipole moment should be 0. Okay, now when experimentally we found out the dipole moment for this is will come as a 3.12 dipole moments. For this compound, dipole moments will come 2.11 D. Okay, therefore in this case the reading is considered as by averaging these two compounds. Okay, 0 and this 3.09. Okay, therefore it is found that this compound, due to electronic repulsion, it's unstable structure. Okay, therefore it's somehow distorted. This structure is distorted and makes to himself as a stable. It's more puckered structure will obtain than this. When we take the experimental reading, it is found that 2.11 D for the dipole moment. Therefore we can predict that it shows the when this mixture is there, and it shows the a large quantity of this compound. Okay, this is by using this dipole moments we can predict the which structure is there when the dipole moments when arises 3.12 delta, then you can say that the compound is definitely there is a AE isomer, and if there is a that type of compound is and 2.11 D dipole moment is there, then we can predict the structures are EE isomers or AE isomers be present there. Okay, when we apply the our one arkel rule for this compound, then these two isomers, among these two isomers, the isomers, these isomers having the dipole moment is theoretical 3.0 is higher, therefore its physical constant is higher when we apply the one arkel rule to this compound. Okay, we have studied this compound for its dipole moments, and we predicted theoretical dipole moments with using the angles, formula of angles theta. By using the formula we can find out its dipole moments. If angle is same, dipole moment theoretically we predicted also 3.09, but this which is matches for the exactly match with 3.12. okay, matches, okay, not very difference is there, therefore this is matches with the prediction one, but this compound is not matches because there is a mixture of AE isomer and the AA isomers. Though it is unstable, but due to this electronic process, it adjusted, bromine molecule adjusted and it's twisted, there is some structure is twisted, therefore its dipole moment also goes on decreasing. Okay, this is all about the study of dipole moments. Thank you very much.